We're going to begin in Chem 1000 with the foundations of chemistry. And at the foundation, really, is the idea that matter is made of atoms, and some supplemental ideas that go with that notion that really form the bedrock basis of everything we do in chemistry. So in this first set of videos, we're going to discuss this bedrock theory. It's known as the atomic molecular theory. And I wanted to start with an interesting question. How do we know that atoms exist? Think about it. How do we actually know that atoms exist? One answer that a modern man might put forth is that we've actually seen atoms. Images like the one you see here are proof positive, we could argue, that atoms exist. We can see little spheres in the image, and that indicates right away, boom, atoms exist. However, in a sense, this kind of begs the question, right? Because we already had to know that atoms existed to create a microscope that was powerful enough to image individual atoms. So we already had to know about atoms to create this image. How did a man like Amedeo Avogadro, who lived in the 19th century, know that atoms exist? Or how did he have good evidence, good scientific evidence, that atoms existed? Back in Avogadro's day, he would have had to make macroscopic measurements. And so the real question is, how do we know atoms exist based on measurements of macroscopic properties, things like mass, volume, and the like? Before we get into answering this question, let's talk a little bit about what was known in Avogadro's time about how chemical substances behaved. There were different types of substances, and this was well established by the time Avogadro came on the scene. The simplest type of substance is known as the elements. These were substances that could not be broken down into simpler components. But it was also known that the elements can be converted into more complex substances known as compounds. So we can combine the elements into compounds, and we can break down compounds into their constituent elements. So this idea that elements, the simplest substances, can be combined to form compounds was well established at the beginning of the 19th century. Pure substances consist of only one element or compound. And we can contrast pure substances with mixtures, which contain multiple pure substances. A mixture is a collection of more than one element and or compound. Back in Avogadro's day, it was unclear how exactly the elements combined to form compounds. And in particular, there were two different camps that we can really imagine here. There was the painter's camp, which thought of the elements like colors in a paint set, such that we could combine the elements in any proportion we wanted to achieve an essentially infinite multitude of different types of compounds, right? We could put in a dash of hydrogen and a dash of oxygen in any ratio we wanted to create a compound of hydrogen and oxygen with just the right ratios of those elements within it. That was one school. Another school of thought contended that the elements were made of discrete particles that could only be combined in certain numbers. So we could only take one chunk of mass of hydrogen and combine it with one chunk of mass of oxygen, for example, or one chunk of hydrogen with two chunks of oxygen, or vice versa. So the Legos here are meant to evoke that image of discrete chunks of mass combining to form compounds. When it comes to macroscopic measurements, the key to deciding between these two possibilities and answering this question really lies in macroscopic measurements of mass, and in particular the masses of elements within compounds, which we can measure simply by breaking a compound down to its elements. So let's take a look at some data we get when we break down a compound into its elements. Potassium carbonate is a compound that contains potassium, carbon, and oxygen. And on this slide, I'm showing you the mass proportions of each element within two different samples of potassium carbonate. The first sample, sample 1, contains a total mass of 100 grams of potassium carbonate. The second sample contains 200 grams of potassium carbonate. And if we look at the two samples, what we can do is we can express each mass as a percentage of the total mass. So we can get a percentage of potassium, percentage of carbon, and a percentage of oxygen. And in the case of the 100-gram sample, it's gravy, right? We're looking at a 100-gram sample, and so we know right away that the percentage of potassium is 56.6%. Similarly with oxygen, we've got 34.7%, and for carbon, we've got 8.7%, adding up to a total, of course, of 100%. What if we do the same with sample 2? Well, what we'll have to do here then is divide the 113.2 by the total mass of 200 and then multiply by 100 to get the percentage. So I'll just briefly show that. So 113.2 divided by 200 times 100%, well, that's just half of 113.2 expressed as a percentage. And as you may have guessed, this is going to come out to 56.6%. If we did the same calculation for carbon and oxygen, in fact, we would get the same percentages, 8.7% for carbon and 34.7% for oxygen. These are all percentages, and we've noticed that at least in these two samples of potassium carbonate, we get the same mass percentages or mass proportions of potassium, carbon, and oxygen in both samples. And in fact, this holds true for every mass of a sample of potassium carbonate. Every potassium carbonate sample includes 56.6% potassium, 8.7% carbon, 34.7% oxygen. If it does not include these mass ratios, it's not potassium carbonate. This leads us to a law of nature called the law of definite proportions. What the law of definite proportions says is that a compound is defined by the mass proportions of its elements. So for the example we're looking at, potassium carbonate itself is defined by the mass proportions of the elements within. It's always 56.6% potassium, 8.7% carbon, and 34.7% oxygen, or it's not potassium carbonate. We can do the same type of experiment for a huge variety of different compounds, and that leads us to the law of definite proportions. So in general, no matter the identity of the compound, all of the samples of a particular compound contain definite mass ratios of the elements, which are reflected in these percentages, these mass percentages that we see that are uniform, independent of the mass of the sample. And if you're already in the mindset that matter is made of atoms, this should make intuitive sense for reasons that we'll see later. But for now, let's try to imagine a world in which we weren't sure whether matter was made of atoms or not. Does this settle the issue? Does this settle the question of whether matter is made of atoms or not? Well, in fact, it doesn't. Even though a particular compound is defined by particular mass proportions, that doesn't mean that the elements must combine in discrete amounts, right? A particular shade of green is also defined by a very specific amount of yellow and blue paint. But still, the amounts of yellow and blue paint that we're able to mix are basically continuous. So we still can't really decide between the paint paradigm and the Lego paradigm just using the law of definite proportions alone. What we really need to think about and consider are the different compounds of the same elements. So for example, we could look at a different compound containing potassium, carbon, and oxygen and see what its mass ratios are and relate those to the ratio we see in potassium carbonate. We're going to do that not with potassium, carbon, and oxygen, but with compounds of nitrogen and oxygen. And one of the first things to notice, which we've alluded to already, is that elements can combine in different proportions to form different compounds. So even though a particular set of percentages defines a compound, the same set of elements could combine in different proportions to form a different compound. Consider the masses of nitrogen and oxygen in the nitrogen oxides that we see below. I've set up the three oxides, A, B, and C, here in a format similar to what we just saw for potassium carbonate. We've got the total mass of 100 grams, the nitrogen mass in the second column, and the oxygen mass in the third column. And so the percentages, again, are definite. Oxide A is always 30.5% nitrogen, 69.5% oxygen. But what we're looking for here is some sort of pattern in the mass percentages. And it's difficult to see just looking at this data. 46.7 doesn't really look like anything special with respect to 30.5, right? So the masses don't appear to follow a pattern. So maybe there's something to this paint model, the idea that the elements can combine in continuous amounts. It's just that oxide A, B, and C tend to be particularly stable proportions of the different elements, but the elements can still combine continuously, and if we find the right conditions, we could get any proportion of masses that we wanted, right? That would be the prediction of the paint model. Something interesting happens when we take each of these masses of oxygen and divide by the mass of nitrogen in each oxide. What we're looking at there then is the mass of oxygen per gram of nitrogen in each of the nitrogen oxides. So what I'm going to do, for example, for oxide A, is I'm going to take the 30.5 grams of nitrogen and divide by 30.5 grams. And I'm going to take the 69.5 grams of oxygen and divide also by 30.5 to get 1.0 gram of nitrogen in oxide A and a mass of oxygen per this 1 gram of nitrogen. And we'll do that for B and C as well to see if we notice a pattern. In fact, we do notice a pattern. We see that oxide C contains 0.57 grams of oxygen per gram of nitrogen. Oxide B contains twice that mass of oxygen per gram of nitrogen, 1.14. And oxide A contains 4 times that mass of oxygen per gram of nitrogen, or 2.28. Interesting. The masses of oxygen per gram of nitrogen appear to come in chunks. This means that there's a unit of mass of oxygen that combines with nitrogen. And if we did the same dance with nitrogen, in fact, we would see the same thing. That's what's shown for you here. Now I've taken the masses of oxygen in each oxide and divided the nitrogen and oxygen masses by that mass of oxygen. So we get 1.0 grams of oxygen, and we get the mass of nitrogen per gram of oxygen in each oxide. And we see oxide A has the smallest mass of nitrogen per gram of oxygen at 0.44. Oxide B has twice as much, and oxide C has 4 times as much. And it's not a coincidence that these numbers seem to match. We go from 1, 2, and 4 on this slide to 4, 2, and 1 on the previous slide. There's a pattern here. And we can conclude then that there's a unit mass of nitrogen that can combine with oxygen as well. This leads us to a law of nature called the law of multiple proportions. The law of multiple proportions is a little bit complicated, but if we think about what we just looked at for the nitrogen oxides, we can understand what it tells us. It says, when 2 elements combine to form multiple compounds, the masses of one element that combine with a fixed mass, like 1 gram, of the other element, reflect simple integer ratios. We're seeing that here. Let's back up a couple of slides. We've got 1 chunk of 0.44 grams combines with a gram of oxygen, 2 chunks in oxide B, and 4 chunks in oxide C. Exact opposite if we look at the mass of oxygen per gram of nitrogen. We've got 1 chunk of that 0.57 grams of oxygen in oxide C, 2 of those chunks in oxide B, and 4 in oxide A. So now that we've recognized the importance of this idea that matter comes in chunks, in particular, the elements within compounds come in chunks, we're then led naturally to the question, well then, what are the smallest units of elemental mass that can combine with each other? Well, naturally then, this leads us to the idea of the atom, a smallest amount of mass that corresponds fundamentally to an element. Anything smaller than that ceases to become an element. It becomes something different entirely. Elements are composed of atoms. And the idea, the concept of atoms had been around since antiquity. And here finally, with the law of multiple proportions, was strong evidence that there were these chunks of elemental mass that were atoms, and they combined in small whole number ratios, 1 to 1, 1 to 2, 1 to 4, for example, to form compounds. So now we have a winner. The paint model cannot possibly be correct if matter is made of atoms, right? Because if matter is made of discrete chunks of mass, we can't combine the elements in any mass ratio we wish. We can only take certain numbers of atoms and put them together, right? And that's what the law of multiple proportions essentially says, that we can only put elements together in specific related ratios that are related by simple integers, 1, 2, 4. That's strong evidence that matter is made of atoms. And that leads us then to the atomic molecular theory, which is based on the law of definite proportions, the law of multiple proportions, and the law of conservation of mass, the idea that all of the mass of a compound is accounted for by its elements. There are 4 principles to the atomic molecular theory, which you see here. The first is that an element is made of tiny particles called atoms. All of the atoms of a given element are identical. So in a sample of pure nitrogen, for example, we have just a bunch of identical nitrogen atoms hanging around that all have the same mass. That's principle 2. To some degree, this is untrue due to isotopes, and we'll talk about isotopes in the very near future. But back in Avogadro's day, for example, the differences between isotopes were so small as to be essentially negligible to him and his colleagues. So for their purposes, all atoms have the same characteristic mass. In the course of a chemical reaction, the total numbers of masses and atoms involved does not change. That's the law of conservation of mass really recast into the atomic molecular theory form. Atoms combine, and they do so such that their total mass remains constant, and the number of atoms present and the types of atoms present remains constant. And then finally, a compound consists of tiny particles called molecules, which contain atoms in simple integer ratios. All of the molecules of a particular compound are identical. So we can take a sample of nitrogen atoms, for example, and we can take a sample of oxygen atoms, and let's say we took 8 nitrogen atoms and 4 oxygen atoms, and we can combine these two to form a compound in which we have, say, 2 nitrogen atoms for every 1 oxygen atom, right? And we would form, in this case, 4 of these because atoms are balanced in their masses and numbers on the reactant and product sides of a chemical equation. And so these little guys that are the essence of compounds are called molecules, and they contain multiple atoms that are combined in small integer ratios, like, for example, we're seeing here, 2 to 1.